So rather than you are going to solve the entire game tree, if you see here for finding out the winner, you will be normally solving the entire terminal node, and you will apply the max score, min score according to the layer. The top layer is the max, next layer is the min, again max. So like that, you can have as many number of layer till the terminal node, max min combinations. Accordingly, you will be announcing the winner of the game. But rather than having the entire analysis of the game tree, this alpha beta pruning is one of the method which can cut off at least half of the game tree. So you need not analyze the entire tree. You can skip the analysis of some of the portion of the tree. So that is the purpose. We are going to introduce a new approach called alpha beta pruning on game theory. But here also you have perfect information about the game. So the entire state transition graph you have in the form of a tree, but you need not going to have a traversal through the entire tree on deciding the winner. So in this particular algorithm, what is the idea is, if a particular move of the player is bad, you can take off any example like 8 puzzle game or a chess board or tic-tac-toe, whatever the game you are taking in consideration. If the you move of a particular player is bad on a particular state, we need not proceed further on analyzing the winner of the game. So on that partial stage itself, you can announce who is the winner of the game. So that is the idea of alpha beta pruning on avoiding the entire tree traversal, and optimally it is going to announce the winner. So for which it is going to introduce two parameter. One is alpha and another is beta. So on the same game tree, you will be doing a pruning on the alpha value as well as on the beta value. So what is this alpha value, beta value is, as we are constructing a max-min layered tree approach, here alpha will be looking always on the highest value we have found so far. Even though you partially viewed the tree, it will be looking the highest value so far we have observed. Whereas beta value will be maintaining the lowest value so far we have observed while playing the game. So that is called as alpha as well as beta. So based on these two parameters, you can think of your earlier fixing procedure. We had a max value fixing as well as min value fixing in the last class. So that procedure is going to be slightly modified by the alpha beta pruning technique, so that the entire tree need not be processed. At the middle itself, we can announce the winner or the loser of the game. So that is the idea of alpha beta pruning. And let me continue further on visualization of this alpha pruning, alpha beta pruning, where the pruning, you are going to cut off some of the parts of the search tree. Rather than searching into the entire tree, you are going to take only the portion. That idea is called as pruning. That is minimizing the search area. You can take that way. Where alpha, I'm going to assume that it is going to maintain the value of the best option for the player one along the path so far. Why so? My player one is always maintained by a positive value. Player two is always maintained by the negative values, right? So positive values are voting towards player one as the highest value, whereas beta is indicating the negative value of the player two, which is expected to be the lowest for making player two to win. So sometime in the tree, alpha may dominate or beta may dominate. Accordingly, you can say that who is the winner of the game. So that is the purpose we are introducing this alpha as well as beta. Based on the partial observation of your tree, you are going to maintain the alpha beta parameter. So let us assume a sample scenario here. It is only a partial tree. We have not shown the right subtree of the particular game. Only left side is being shown. So now there are three terminal node being given with a value of 3, 12 as well as 18. And the layer architecture is, the topmost is the max layer, the next level is the min layer, and this the terminal layer, right? So you will be doing only a min operation here as well as a max operation on the root of the game tree. Now what happened? Automatically these three values are given. So the intermediate node value will be obviously chosen to be the minimum, as all nodes are observed in the terminal. Okay. So now what will happen? The intermediate node value will be taken to be 3, and the max layer value may be expected to be greater than or equal to 3 because this is the only partial observation of the tree. Maybe on the right side it may have some more sub tree. So if they have a value above 3, your max node will be having a value greater than 3. Otherwise, it's expected to have a value of 3. So this is the partial observation, and we are looking on the minimum somewhere, we are looking on the maximum somewhere. So when I say minimum, it is a kind of a beta pruning. When I say maximum, it is the alpha pruning. I hope it is little clarified now. Let me further give a partial tree again. It is also still partial. I'm giving one more successor of my root node with a node value C, but the terminals are again not fully available. Only one value is available, the other values are unknown. Some unknown value is being given. But as it is doing a min, it is expected that the C value is going to be either less than or equal to 2. Why less than or equal to 2? Can anyone suggest why I'm saying it is less than or equal to 2? Yes, how you are writing here as less than or equal to 2? Can you tell me the reason? Someone? Why it is less than or equal to 2? Among this, what I'm choosing here as the C value? Hello, are you listening to me? Among these value, what is the operation I am doing? Am I doing a min or max? Hello, அம்மா நான் பேசுறது கேக்குதா கேக்கலையா? Are you all there or not?
மேம் கேக்குது மேம்.
எஸ்மா? ஹலோ, ஏதோ சொல்ல வந்தியம்மா, சொல்லு, சத்தமா சொல்லு.
மேம் நீங்க பேசுறது கேக்குது.
It is choosing what? Among the three value, what it is choosing?
2
Minimum or maximum?
மினிமம்.
Minimum. Very good. So as it is a min layer, it is choosing the minimum. So the unknown value may be less than 2 or may be greater than 2. We don't know. We don't know the information about the unknown terminal nodes. Okay. So when I compare all the three value, it may be less than or equal to 2. We don't know whether such node is available or not. If such terminal node is available, C value will be less than 2. Otherwise, it will be equal to 2. So that is why we are writing here the value as a range, which is less than or equal to 2. But when you are going with a maximum, as it is already 3, whatever the value of C, it is ignored by the max layer. It will choose only the maximum. Suppose I have one more terminal here, which I take a value again. Okay, now suppose I give here 1. So what may be the expected value for the D here? Again, I apply the same principle. It will be either less than or equal to 1 only. Okay, so if I know the terminal node, I need not bother about the entire subtree for considering my max layer because it is already lowest than the other layer value. Okay, so even though some of the nodes are unknown, if at least one path is available, so here on the terminal, you have one additional path. On the terminal, you have one additional path. But you are skipping as many number of terminal nodes. இங்க எத்தனை terminal nodes வேணாலும் இருக்கலாம். அதை நான் என்ன பண்ணிடுறேன்? Skip பண்ணிடுறேன். The reason is it is choosing the minimum and then it is choosing the maximum. So the minimum is lower than the highest minimum over here. So we can skip some of the partial tree. You need not go through the entire tree. So that is the idea. So the same way, I have written 1, but here they have written 14. So for the 14, as it is choosing the minimum, whatever the other terminal node, it will be the value which is less than or equal to 14. As it is less than or equal to 14, and your max value is going to be uh, greater than or equal to 3, I am writing, but it may be less than or equal to 14. The limit is from 3 to 14. We don't know. Okay, and the range is from 3 to 14. So that is the idea. So this way, you can suggest. Suppose some of the states are further available. Apart from 14, I have one more terminal node 5. Now what happens among them? It will choose the minimum. So rather than less than or equal to 14, it will be coming as less than or equal to 5. As it is less than or equal to 5, this limit will be limited to 3 to 5. Okay, so it will be less than or equal to 5, but above 3. So that is the idea we are getting. So this way, this thing is working. And how are we going to apply this pruning on a partially available game tree? So now you can see here, let me just adjust the tree for your visibility. So here what is available is, you can see in the partial availability of the value, -1, -2 is fully available terminal node. But here there is a question mark, and here there is a 4, and these all 4 are blank. Okay. So now what happened? I am going to identify with the help of my alpha beta pruning. So with the pruning on beta. So what it happened on the node V, we are going to apply the beta pruning. So beta pruning at node value V. So what is the value we are expecting at this particular node is, when you are taking the layer operation, this is max as the first layer, then it is minimum at the second layer, and then again it is a max at the third layer, right? So it will be choosing the maximum between -1 and -2. So this partial node, sorry, this terminal node will be contributing to the intermediate node with a value of -1 by comparing with the -2. Now my beta pruning at the node V, that is what is beta? I am choosing the lowest, right? So the choosing of this lowest value is decided by its terminal, which is unknown to me, as well as the 4. So it may be expected to be less than or equal to 4. Suppose this value is 5, it is expected to be 4. This value is 3 or 2, it is expected to be less than 4. So this is the idea. But when you are comparing with this min will be choosing one among the minimum only. So obviously, it is decided by the question mark. Whatever the value available here, that will be chosen over here. So it is less than or equal to -1. So that is only it is written here. Beta pruning at node V is going to give you a value which is less than or equal to -1. So yeah, so that is the reason. How are we doing the pruning? Even though I have intermediate nodes are not available with a proper terminal, I can conclude with a comparison of max min layer. So accordingly, I can take a suggestion for my this min operation with a value of less than or equal to -1. Okay. So by comparing this 4 as well as question mark, I filled the intermediate node. By comparing these two with the min operation, I have come out with a suggestion of less than or equal to -1. So this is called lowest value pruning. So otherwise, I call it as a beta pruning. Okay, it is happening at the min layer. So it is called as beta pruning. The similar way, you can do it for the max pruning also for the alpha value. So where you are going to pass this over the top layer. So let us see what is happening. So here what happens, I am filling again the min as well as max. So max, min, max. So -1, -2, -1 is the maximum. So let me use different color so that you can understand better. So this is the max layer -1. And here I have both the question marks. So I put question mark. And here I have 6 as the maximum. One is -5. And here 7 as the maximum. Again, I will be choosing the minimum. So this will be filled by 6. And this is unknown, but it is -1. I have to fill the minimum. As we did the beta pruning, the value will be less than or equal to -1. So what is the top layer? Again, it does the maximum, right? So at node W, we have an unknown value which is less than or equal to -1 only. So we are applying the alpha pruning here, because one node is known value, this is unknown value with a relation of less than or equal to -1. So we apply here alpha pruning, because here I am making a decision on max. So what do I do? Whatever the value of w I have, my value of w is less than or equal to -1, which is being compared with the value 6, which is choosing the value as a 6. So as a result of alpha pruning at this particular position, my next top layer will be getting the value as 6. So even though it is having some unknown number, you can see here both of the terminals are unknown, but still it is capable of contributing on assigning the value for the next layer. So this is the idea called alpha pruning. I hope it is clear. Puriyalana kelu, I may move further. If you have any doubt, please ask me as of now. Clear, Arkriya? Any response can I have? Is it clear, or what you do is just max min, that's all. ரொம்பலாம் பயந்துக்க வேண்டாம். ஒவ்வொரு டைமும் நீ என்ன பண்ற, அந்த பர்டிகுலர் நோடுனுடைய என்ன ஆபரேஷன், என்ன ஸ்ட்ராட்டஜின்னு பாக்குற, அதுக்கு கீழே கனெக்டா இருக்கிற டெர்மினல் நோட்ஸ் எடுக்கிற, அதுல மேக்ஸிமம் வேல்யூ ரீப்ளேஸ் பண்ற. அன்னோன் வேல்யூவா இருந்ததுன்னா ரிலேஷன்ல சொல்ற, அவ்வளவுதான். சரியா? இது இப்போ ரெண்டுமே அன்னோன், அப்ப நான் கொஸ்டின் மார்க் அன்னோன் தான் வைக்கிறேன். பட் இந்த ரெண்டுக்கும் நான் வந்து இங்க ஆபரேஷன் வந்து மினிமம். அப்போ இந்த வேல்யூ என்னவா இருக்கலாம்? சப்போஸ் -1 விட லெஸரா இருக்கலாம், ஆர் கிரேட்டரா இருக்கலாம். ஸோ த வேல்யூ இஸ் எக்ஸ்பெக்டட் டு பி லெஸ் than or equal to -1 அப்படிங்கிற ஒரு டெசிஷனுக்கு வரேன். இஸ் தட் ஃபைன்? ஷால் ஐ மூவ் ஃபர்தர்?
Yes, ma'am.
Okay, good. So we can able to predict the values of our tree, even though the terminal nodes are partially not available or not observable. We can able to predict the overall score of the particular game. So the last game நமக்கு என்ன வேல்யூ வந்ததுன்னா, we got the maximum value over here. And so இது வரைக்கும் நான் பண்ணது, அதாவது மின் லேயர்ல நான் பண்றது பீட்டா pruning. I mean then max sorry இந்த max layerல வந்து unknown இருந்ததுன்னா you will be doing a beta pruning to fill the min layer. And similarly if you are not having a known value on the min layer, you will be doing a alpha pruning on filling the max layer. So this is the idea. So this way you are doing the pruning operation. So let me move further on writing a modified recursive implementation of alpha beta pruning as compared with our last class min-max algorithm. So in the min-max algorithm, what we did is, if the player is 1, we started with a -infinity, and for each action, we have taken the max score of v comma value of successor of state comma action. This was the only parameter we had earlier, but now as it is alpha beta pruning, we are introducing alpha value as well as beta value. So what is this alpha value? Beta value is the highest value observed so far is called as alpha. Lowest value observed so far is called as beta. Okay, so this is the two parameter. So according to the earlier example, maybe in certain cases, this value will be 6 or -1 according to the so far observed maximum, so far observed minimum. Okay. So now what do I do? Before I assign or return the value v, earlier we just returned the value. Now what do we do? Before we return the value, we are comparing that value with the beta. So if the current value is greater than or equal to beta, then only I am returning v. Okay. Otherwise, what do I do? I may be updating, otherwise I am updating the alpha with a max of alpha comma v. So what does it mean is, if the values I am observing now on a particular state due to a particular operation is having a greater value than beta, because beta is the lowest. It is the lowest, right? So far observed lowest I'm maintaining, and alpha is the so far observed highest. So currently what I observed is the v. Okay, currently I observed what is the v. So what do I do? I take the value of the current successor, and that value I am comparing with my v. I choose the maximum between all the 4 parameter, that is the lowest, highest, current value as well as successor value. So while I am comparing the 4, as it is -infinity, you may be getting a value v or alpha. So when do you get alpha? If V is less than alpha. Otherwise, if V is greater than alpha, you will be getting the V over here. Okay. Suppose I say my alpha is 6, my V is 7. So I'll be getting here the 7 as the result. Suppose my highest value itself is minus 6, but my V is 7 means still I will be getting 7 only. But if my V is minus 7, but highest is minus 6, I will be getting the value as minus 6 over here. So that is the max operation here. So now what happened? I'm comparing my V value with the beta. So V may be dominated by the maximum among them. I'm comparing that with the beta. If it is dominating or equal to beta, I will be returning the V. Otherwise, I will be updating my alpha as the new maximum by comparing alpha as well as V. You take the earlier scenario 6 as well as 7. So when alpha is 6, my V is 7, it will be updating alpha also. So the highest value observed so far is changing here. Okay, then only I'm returning. So 2 point I'm doing extra here. I'm comparing with the 2 more parameter and I'm updating by doing a comparison. Similarly, I do it for the other side, for the beta pruning also. We take a V value as a positive infinity, and for each action, you are using the min with the 2 more parameter alpha and beta. So now the lowest may be either beta or it may be current V, current value of V. Okay, among them, anyone may be chosen as the minimum. And if that V is less than or equal to alpha, you are going to return that V value as such. Otherwise, what you are doing is you are updating your beta as the lowest minimum. So this is the way you are comparing your alpha beta pruning on every state of transition within your graph. Okay, so this is the idea of alpha beta pruning. So with this, we are trying to solve the real world problem uh, by applying this alpha beta pruning. So before that, let me conclude what is the feature of this alpha beta pruning compared to your min max approach. So without pruning, when I am doing with the min-max approach, I need to have, as I told already, I have a breadth factor B and I have a depth factor M. Okay. So I'll have to examine every nodes of my game tree. So which will be having a worst case complexity of big O of B to the power M. Whereas when I am applying this alpha beta pruning, it will be decided by the nodes which are I am going to consider first. So am I going to consider only the particular subset of successor, or am I going to consider the entire successor list? So accordingly, this will be decided. So normally what do? Is they choose a random successor. As you recall the earlier diagram, we introduce first successor B, then second successor C, then we introduce third successor D. So like that, you are not examining entire successor. You are going to examine only the randomly chosen partial successor of that game tree. So obviously, it is going to be reduced by 3/4 of your original number of iterations on passing through your game tree for announcing who is the winner of the game. Like that, you can choose different algorithm either for choosing a random successor algorithm, or you can go with the best successor first algorithm, and that will even lead to even minimum number of node selection on your game tree. So this is the idea of alpha beta pruning. And when I am choosing a best successor, I may have to make use of some heuristic function. So I will be introducing one such heuristic function while we play a chess game. So according to the best successor, it will be calculating the heuristic. Based on that, it will be telling which player is in the forward towards winning or losing. So this is the idea. So let us try to apply this min max with a alpha beta pruning for a popularly known problem called tic tac toe. So as they told, they are going to apply the practical heuristics for choosing the next successor. Here also, I'm going to elaborate that with the help of a basic example. So first, let us understand what it is doing. Everyone know the tic-tac-toe game. There is a player X and there is a player O. So there are 9 position on the board. You can count up the number of position: 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So the players are alternatively placing their coin in the shape of either X or O. And now you can take up this board situation where one X is placed and one O is placed. Now let me try to understand the winning strategy for player X. The player X may further put his coin in this row in order, or he may be putting in this column in order, or he may be putting in the diagonal in order, otherwise in this diagonal, or in this way. Now you count up the number of possibilities the player X has to win. You can see, and this way also he can move. The X can place his coin, assuming O has not placed anywhere. So how many possibility he has is 1, 2, 3, 4, 5 as well as 6 possibilities are there. So this is the number of possible winning path for player X. Similarly, the same board position I am taking for my player, Y, O. For him, as he has his own possibility of moving, first one, second possible path, third path, fourth path, as well as fifth path. So he has 5 possible paths. Okay. So what he don't have is this diagonal he cannot win because already X has placed. So this diagonal is missing for O compared to your X. So he has only 5 possibility to win. Now my evaluation function heuristic will practically assign a node value for each of the board positions. The same board position only I have calculated for X, I have calculated for O, right? So this is for the number of winning chances for player X. This is the number of winning chances for player Y. The difference between them is taken to be the heuristic function for tic-tac-toe game. So accordingly, you may be applying the min-max further. So the terminal node will be given such value. Accordingly, the intermediate nodes will be choosing the minimum as well as the maximum. Okay. So now you work out how it is going to be 4 as well as 6, 5 as well as 4. So as like this, you must be able to tell how it has 4 possibilities only, how O has 6 possibilities. Suppose you take X, it has only 4 possibility, they say. It cannot go through the middle horizontal line. X can go by first horizontal, X can go by second horizontal, X can go by this vertical, or it can go by this vertical. Yes, it has only 4 possibility as of this position. Okay. Similarly, for O, you can take up, it can have 6 possibility. Diagonal, all the diagonal are possibly available for O. So middle vertical is available, third vertical is available, first horizontal is available, second horizontal is also available. So totally it has 6 possibility. So on this particular board position, our terminal node value is assigned to be -2. And for this position, the terminal node value is assigned to be 1 based on the game heuristic. Now, uh, given different such positions, you can able to calculate your heuristic value on the terminal node. After that, you can apply the maximum theory as such to calculate the possibility of player 1 or player 2 towards winning. So let me expand this with some more intermediate node value and level. This is the max level and this is the min level. Assuming that there is only 2 levels are shown here with a terminal node. So all these are terminals. So here this terminal has 5 possible states and this terminal has 2 possible states, and here this terminal has another 5 possible states. Okay. As usual, you apply the number of possible win for X as well as number of possible win for O on every board position based on the earlier practical heuristics. So it revealed that in this particular position, both of them are having 6 possibilities. Here also both of them are having 6 possibilities. Here X is having 5 possibility, O is having 6 possibility. So when you are making a difference between them with a sign, okay, and there are some value with a minus, there are some value with a 0 count, there are some value with a positive number, there are some very lowest negative number, there is very highest positive number. If you compare the 12 state, it ranges from -2 to +2. If you compare the heuristic range of this 12 terminal state, they are ranging from -2 to +2. So here the lowest is 1 and here the highest is 2. Whereas here the lowest is -1. So -1 is the lowest and the highest is, sorry, -2 is the lowest and 0 is the highest here. Minus 2 is the lowest and 0 is the highest. When you are coming to this side, there is a minus 1 which is lowest and 1 is the highest. Okay, so this is the range of your each terminal positions. Now, according to your min max tree, it apply the min operation. So you can see here, it is choosing the minimum among them. The minimum is minus 1. It is coming over here. Here, the minimum is 1 is coming over here. So these are the heuristics. From the heuristics, it is choosing the max as well as min intermediate values. And here you are having min as the minus 2. Again is the max layer, which is choosing the value as 1. So what it indicates is when the player has a kind of a move like this, player 1 move, this is player 2 move, and this is again player 1 move. And if the player 1 has done this, if player 2 has done this, player 1 has the possibility of winning. So like that you can come out with the solution on any one of the player 1 move. He has a possibility of winning according to this state transition graph. So yeah, so this is the way in which you are calculating the terminal node value, and accordingly you are filling the max min for doing the fill up. But here, do I have to go through the entire tree is the question. Suppose I partially neglect this portion of my subtree. When I do the alpha beta pruning, what will happen? It is choosing minus 1 and my 1. This is unknown. I'm just skipping this. There is a terminal, but I am skipping this. So when I am choosing the maximum, among them it will be choosing the maximum. So the value will be greater than or equal to 1. Anyhow, the positive number is voting for player 1. So whatever the value, I can announce that player 1 is going to win. So even though this partial subtree is not at all observed by the game, I can omit the subtree. Still, I can guarantee that player 1 is going to win. Are you able to follow? So this is the idea of alpha beta pruning. You can eliminate the traversal through certain subtree. Still, you can guarantee who is the winner of the particular game. So this way we are doing the alpha beta pruning. And one similar example is being given here, where the here you can see terminals are not given, but the values alone are given. Minimum is 0, minimum is 1, minimum is 0. Minimum is 0 means both are having a same possibility of trial. Both are having same possibility of trial to win, right? So among them, it is going to choose the maximum. So the maximum is chosen to be 1 here, as every one of them are having a 0. We know this value, we don't know about the terminal number, but we know the heuristic information for the min layer for all the node. So there you can continue on announcing the winner without further analysis on the subtrees of the particular graph. So this way you can limit the number of traversal through the subtree when you are doing alpha beta pruning. So it is one best example for solving it. The second example we are taking is sometime the alpha beta pruning may be too difficult on identifying the value of the intermediate layer if the problem is a very biggest one. Even the tic tac problem will take 9 moves, right? So there will be 9 levels of the depth of the tree. So there are certain chessboard game. They will be having more number of levels. Both the player will be having 16 coin. So they will be keep on moving the through the game. And the Go game also has lot of movements. So like that, you will be having lot more intermediate stages that will lead to terminal deepest terminal. So in such cases, the number of maximum layer will be keep on increasing. So to avoid handling of alpha beta pruning on such a deepest tree, they are introducing some more simplest way on calculating the success of the particular player by limiting the depth of the tree. And at every depth level, they would like to calculate the solution rather than going to the deepest terminal node as like your min max. It is trying to calculate the solution at the limited depth itself. That means at the level of depth 3, at the level of depth 4, at the level of depth 5. Like that, it may be calculating the solution. And it will use some game heuristic. If that heuristic is meet out, on the particular limited depth itself, you can announce the winner or you can announce the loser. This is happening in the chess game. Even though there are certain moves are there, it will not allow the player to play. It will say that moves are over, something like that. So this is the last move. You cannot proceed the game further. So like that, it will be announcing with the help of a evaluation function. So how are we going to use the evaluation function? It is decided by the number of I mean node values available on your game tree. Okay, so that is going to be defined as a evaluation function. For an example, in a chessboard game, the for evaluation function definition, I am going to make use of certain heuristic information where for every number of queen, it is going to be given a point value as 9. So obviously we have only one queen in the board. So if the player has a queen in the board, his score will be 9 into q plus number of rooks he has will be multiplied by the value r. Sorry, 5. So number of rooks are r. It will be multiplied by the point value 5 plus number of bishops. Maximum 2 bishops are allowed, and one may be already lost by the player, let us assume. So it will be 3-point valuation, 3 into number of bishop. It may be 3 into 0, it may be 3 into 1, or it may be 3 into 2 if both the bishops are active on the board. Similarly, for knight also, they give the score point as a 3 into number of knights. Suppose I represent by k plus pawn. Okay, for each pawn, it is going to give the value as 1. So number of pawn I'm having as p. P into 1 is p only. So this is the evaluation expression I am getting for deciding on the intermediate state or on the limited depth who will be the expected winner, who will be the expected loser. அப்போ ரெண்டு பிளேயருக்கும் நான் என்ன பண்ணுவேன், I will be evaluating this function. I may be comparing their value. Is it less than or equal to or greater than or equal to? So accordingly, we can say whether player 1 is going to win or player 2 is going to win on their number of coins. What do they have? So yeah, so this is the heuristic. So you are going to calculate the difference between two players' material value. If it is positive, player 1 will win. If it is negative, player 2 will win. So this is the idea. So, uh, the same equation what I have written is mentioned here. So rather than I mentioned knight as k and they have mentioned as n, nothing wrong in it. So like that you can now calculate for a particular partial stage of the chess game, you can evaluate the function. And for the black player, now you can see this is the king position. He has a knight. He has a pawn, one pawn. He has one rook, right? So like that, he has one bishop. So now you can calculate the value for black player having one bishop, one rook, and one pawn. So you apply over here. One bishop means 3 point, one pawn means 1 point, one rook means 5 points. So he has 9 points, right? So black player has 9 points as of now, and white player has 3 pawn and one knight and one rook. So for the knight, you will be given 3 point, and for pawn another 3 point. 3 into 3, 3 into 1, 3 plus 3, and for each rook 3. Again, it is 9. So they are having equal evaluation value as of now. So on this particular position, you cannot decide who is the winner. So you need some more strategy on or moves on further level. So based on the depth level, further if you move, so white, suppose assuming that this is the white's move, and it is taking a move on applying the code of RD8. So what is this RD8? You have to know the a way in which they are playing the game. I just have some simple example. I hope my screen is still visible. I am using a link here. Okay, it is protected by our server, but still what we have tried to explore you is these are the code being used by the uh, chess game on indication of the move. These are the code. For every action they are using a code. Okay, so accordingly the game tree will be having a decision towards the winning for the either white player or for the black player. Okay, so this move was taken by white player on the current position, followed by kb7 move was taken by the black player. So like that you have various notations are there, and accordingly you can finalize who is the winner. So this is the way they are calculating that terminal value by the evaluation function on after 3 or 4 moves. So that move may be either taking some of the black coin or the some of the white coin, and he has two more suggestions, either one this way or this way he can go. So like that you can come out with the evaluation function on these two, and accordingly you can decide as a white player based on the evaluation function. You can choose any one of the terminal moves. So this is the idea of heuristic function on evaluating the current board position, and informing the player what would be the better strategy of move in order to win the game. So one says, there are certain clues are being given to the player by the machine. It may be saying that if they are having a king, they may be having more possibility of winning than having the other I mean other coins. Okay, so this is the way. And apart from that you can even play the game with a random move also, rather than having a structured move like this with the evaluation function. So here for every move you have an evaluation function. You are having a structured formula, and you are calculating the winning strategy of the particular state for both the player based on the evaluation function. And sometime on the nature of the game, some you may be doing a random movement also, because the game like rolling the die. So there are two players, they are rolling the die. So the combination they are getting, one player is rolled 3 and the second player is rolled 2. One player has rolled 3, another player has rolled 4. Like that you have different combinations. And this is pure random. It is randomly being distributed between the players move. And here again you can even able to construct your game tree in such a way that by using a same max min layer approach, what you are calculating as the winning strategy here is the probabilistic winning. So uh, first one is the game player and second was the natural player who is nothing but the human. So they have a probability of winning 50 percentage on this path, 50 percentage on the other path, whereas here they have only 40 percentage on the left subtree. They have 60 percentage of strategy of winning on the right subtree. So like that the probabilistic score is being assigned on the tree path on deciding who is the winner of the game. And it is decided either by the fair dice or it may be unfair dice. Sometimes the dice may be unfair. They will be having more probability of bringing winning only to the player 1 rather than player 2. Okay, so like that also it may vary. So you have to choose the algorithm according to the nature of the game. And so you can see here how the value is being chosen between the two player on the intermediate node. So this is max layer, min layer, again max layer. So you will be choosing the maximum so far observed on the uh, first player as well as the second player. So like that the values are being uh, chosen over here, and you will be collecting them together as it is having a probabilistic score 50 percentage. The values are being taken 1 plus 3 4 divided by 2. It will be taking the score as average of 2, and 3 plus 4 as 7 divided by 2 you are getting 3.5. So like that the scores are being assigned on the intermediate node, and finally whoever the player 1 and player 2, so whoever has the highest score will be assumed to be the winner of the game. So this is the different strategy on random move based games. but there also they are having a terminal node, they are having a likelihood score, and those scores are being weighed on different probabilistic score on the path. So that is the strategy here. Yeah, so this way you can do the calculation on announcing the winner. So with this, let me stop today's discussion. Maybe one more topic we have on second unit, so that we will discuss in the next session. With that, we will conclude the second unit.